So this is chapter 5 on thermochemistry. This will talk about heat and work to some extent. Here's your table of contents. First law of thermodynamics. We're going to talk a little bit about that, and we'll talk about thermodynamics being the study of the changes of energy or transfers of energy in chemical reactions or physical processes. In thermodynamics, we try to address 3 fundamental questions. We'll focus on bullet point 2 the most, 1 and 3 just a little bit. Will 2 or more substances react? If they're mixed, we'll at least talk about some specific conditions. If they do react, what energy changes or transfers are associated? That one we're going to focus on a lot. And if the reaction occurs, what extent does it occur? There's a second thermodynamics chapter where we'll focus on that a bit more. In exothermic reactions, we get a net release of energy to the environment. For example, combustion of propane is exothermic. Combustion reactions are exothermic pretty well universally. They will release heat. In the case of the propane, you react it with oxygen. You produce 2,220 kilojoules of energy per mole of propane that burns. Methane is also exothermic. We burn that in presence of oxygen. We produce 890 kilojoules of energy per mole of methane that burns, where methane's in natural gas. But they're going to release heat and light to the surroundings, any form of energy to the surroundings. And that happens because the products are lower in energy than the reactants. If we consider a graph that looks at the combustion of methane, where the y-axis is energy, the x-axis is just some arbitrary coordinate that indicates the progress of the reaction. But we have our reactants on the plateau here. We have to get it over some energy barrier, which we'll call the activation energy, because, hey, methane doesn't burn just all by itself. Usually so it needs some ignition source. That's going to provide that energy required to get it to go. Notice the products are at a lower energy. The difference is the amount of heat released to the environment. In this case, 890 kilojoules of heat evolved from that reaction. If we want to look at endothermic reactions, those tend to absorb energy in the form of heat. If we look at barium hydroxide octahydrate in the solid phase and we mix that with ammonium chloride in the solid phase, it is somewhat endothermic, and I'll produce barium chloride, water, and ammonia. But it's going to take just a little bit of extra energy to be added to get over that barrier. One way we can tell that is that if we put a little drop of water on that block of wood in that second picture, then mix the solids together on that, we can pick up the wood because it's actually cool enough to freeze that little bit of water we put between the beaker and the block of wood, indicating that the reaction is absorbing heat from its surroundings. Absorbing heat and being endothermic is not a favorable condition for a reaction to take place. If it's a small enough amount of energy, it will take place. There's some other factors that go into it. Exothermic tends to be favorable, endothermic tends to not be. But there are other factors to consider. So let's look at the reaction profile of the barium hydroxide with the ammonium chloride. And if we look at the graph, we can see we've got another peak. Again, that's your activation energy. It's a steeper hurdle to climb because I've got to put that difference in energy in. Notice the energy of the products is higher than the energy of the reactants, indicating a net absorption of energy over the course of the reaction. Now, when we start talking about heat of reaction, delta H, and we'll talk about that a little bit later on in more detail, but if that is a positive, that means heat is going into the system. That is endothermic. If it's negative, then the process is exothermic. We kind of look at Here in this question, we've got two different equations, and we want to consider whether each of the reactions is endothermic or exothermic. We got the acid-base neutralization. Those tend to be exothermic, and we can see that the delta H is negative, indicating that the reaction is in fact exothermic. In the case of B, we can see the 164 kilojoules is written on the reactant side, so that would be endothermic. It could be a number of kilojoules or the word heat, anything to indicate which way the reaction is going. So there are two basic ideas for the importance of a thermodynamic importance for a thermodynamic system. The chemical systems tend towards a state of minimum potential energy, which is the one we're going to focus on just a little bit more. Water flows downhill, objects fall when dropped. For example, those are two examples are based on gravitational potential energy, where that energy is equal to mass times the gravitational constant times the height of the object. Now, systems can also tend toward a state of maximum disorder, and we'll focus on that a little bit more for the second thermodynamics chapter. But a mirror shatters when it drops, but it doesn't reform. You can scramble an egg, but it's next to impossible to unscramble it. Food dye will disperse, but it's hard to get that drop of food dye out of the water. The more ways you can arrange a system, the more likely that is. Think about shuffling a deck of cards. To get everything ordered by card and suit, like you get it out of the box, would be an unlikely situation after you shuffle. So the law of conservation of energy is also a statement of the first law of thermodynamics. The energy of the universe is constant. Energy is neither created nor destroyed. In chemical reactions or physical changes, it's just transferred from one form to another form. Here are some thermodynamic terms. Substance involved in a chemical reaction or physical change that we're looking at is called the system, that little bit of the universe that you're interested in. The chem lab, it's likely, in this course, it's likely to be a simple system like chemicals inside a beaker that's reacting. Everything else is called the surroundings. We can measure heat transfer by measuring the heat of the system or the immediate surroundings and talk about whether the heat is going in or out. The systems plus the surroundings would be the universe at large, although we tend to be measuring the immediate surroundings and not the bulk surroundings. There's sets of conditions that we end up calling the thermodynamic state of the system. For example, that could equal the number of moles and identity of each substance, the physical states, that is whether it's solid, liquid, or gas, or is an aqueous solution, the temperature and the pressure of the system. We'll consider a lot of those in many cases to determine thermodynamic properties. Many thermodynamic quantities are what they call state functions. That is, it's based on the initial and the final condition, and it's independent of the pathway we use to get there. Like if you drive from work to school, there might be more than one route where one is more direct than the other, but your sort of distance from home to work as the crow flies is the same. Or like getting up to the top of a mountain by two different paths where one might be more difficult than the other, but the height from the bottom of the mountain to the top of the mountain is the same. However, your effort may not be, so the effort would not be a state function. And you could calculate the change in the energy, gravitational potential energy, using the gravitational potential energy formula, for example. Now, some examples of state functions are temperature, pressure, volume, internal energy, which we'll talk about, delta E. Delta H is the heat of reaction or the enthalpy. The S or the entropy, which we'll talk about more in that next chapter. Examples of non-state function would be things like moles, heat, work. If we're only interested in the initial final condition, any state function can be expressed as the change in that quantity is equal to the final condition minus the initial condition. If it's positive, then that quantity increases. If it's negative, that quantity decreases. So let's look at which of the following are state functions. Heat, change in Q, change in temperature, enthalpy, moles. The heat or Q is not a state function, as we can see in that paragraph above. It's different than the heat of a chemical reaction. Change in temperature is a state function. Enthalpy, the delta H, is a state function. And moles, as stated in the paragraph above, is not a state function.